curves, okay? So parametrically defined curves, let's write this down first. You saw these in Math 2. You saw them in Math 2. You only did parametrically defined curves in the context of lines. I just checked that with Mr. Fullars. Parametrically defined curves. Let me start with an example, and then we will sketch it. We'll talk about what the heck is the purpose of parametrically defined curves. I know that you guys are all burnt. I know it. I see you. I hear you. I hear you. I will bring in sustenance and a surprise on Friday. I promise. I know. It's no joke.
I'm so excited.
No, it's no joke. Was that sarcasm? Daniel, how dare you? How dare you?
Oh, I would never do that.
Oh, please.
That was so funny.
Okay, everyone. This is an example of a parametrically defined curve. You are going to notice something. Curves that are defined parametrically are curves where the independent variable is time, and x and y both depend, not time, sorry, on t, okay, where x and y depend independently on t. A couple of vocabulary, okay, I'm being too distracted and interrupted. This variable t here, the independent variable that x and y are dependent on, it's often referred to as the parameter. Okay, the parameter. When you are looking at parametrically defined curves, one of the reasons you have is, what is the whole point of parametrically defined curves? What does it allow you to do? What can you graph with these? Parametrically defined curves allow for the graphing of curves that are not what, Albert? I see your hand over there.
I was about to ask you, so I'm going to guess functions.
Yes, okay? When you describe curves parametrically, that allows us to graph curves that are not functions of x, which means they are not curves that pass the vertical line test. Okay? Yes, Daniel.
So, these parametrically defined curves, so are they used to graph the same curves we see as ones that we need to use implicit differentiation for?
I promise I will answer all those questions, but you're on the right track.
Okay.
Yes, I promise I will answer all questions. I will never leave you dangling or hanging or stranded, okay? You'll recognize this from back in the day. Back in the day, you used to make something called a T-table.
Oh.
Plugging and chugging,
I love T-tables.
okay? The T-table now looks no different, except for the fact that we have a T, okay? So, all right, I'm going to actually be very specific. Gentlemen, as in not the ladies. There is a time at which you are getting in my way. And by my way, I mean everyone else in the classroom as well, who is trying to stay attuned to you. It's only like 3 of you, but you've got to know when to rein it in. That message, picking up on that point where you have to rein it in, seems to be a very gender-specific cue that is being missed. And this is going on live recording. Everyone on YouTube will know this. In this class, I am noticing a very gender-specific failure to acknowledge the social cue of reining it in. What does reining it in mean? Wow!
Ouch, can I get into this?
Wow! Arusha just threw it down. Realizing your remarks are not that witty. What else does it mean? I would have to concur. That is very sharp and to the point. What else does it mean to rein it in? Realizing what? It is time to stop. Okay? So that is the time. We are there right now. Let's proceed. Are we ready? Very good. All right, here we go. Let's sketch this function. Now, the fact that I chose these graphs here was purposeful because I know you all remember we're looking at t values. I'm going to stay in radians. I'm going to pick these values conveniently. Arusha, I have to say, you know what? Only you could have done that in that deadpan fashion. That was pretty awesome. Okay? If we go through and sketch these, look at these points, we're going to get some points here. What's the cosine of 0? It is 1. Very good. 6 is x. Okay? 0. I'm going to let you turn to someone next to you and rip through the rest of this t-table. Go ahead, fill it in. Let's go. Let's see it. Realizing that your marks are just not that witty. That going in my book of quotes, Risha, that is a fantastic thing. Number 1 quote from a student was, "What the function, Daniel? Please stop speaking." That was... What was that? In history? Who called everyone ugly? Arusha. Okay. Arusha speaks the truth. She does not lie. I know she takes her words very, very seriously.
If you're comment, but she's not distracting class even further.
I think not. I think she was just speaking truth, Thomas. She was just speaking her truth.
Alright, so when Arusha speaks the truth, she's fine, but when I speak the truth, I'm only a preacher.
I'm ready. X and Y for pi over 6. Go, go. Hello? Values? Oh my word. 3 radical 3, right?
Yeah.
Yes, 3 root 3. Everyone all right? All right. What's the y coordinate? Okay. Can we hit the rest of these? Go ahead. What's going on here? Maya, do you have pi over 4 as x and y for me? Go ahead. Yep, and y it is? Uh-huh. Okay, pi over 3, I'm ready.
X equals 0, y equals -2.
Is that right?
X equals 3.
X equals 3 I have too.
3 and yeah,
Let's see. Pi over
I have 3 and
draw a
3.
circle.
Everyone okay?
Yes.
Oh, whoops, sorry, I made a mistake. Excuse me, I looked at the wrong thing. Look at the wrong thing. Sorry.
Oh,
Pi over 3.
I said this.
Yeah, sine of pi over 3 is what?
Sine of pi over 3 is root 3 over 2.
Right,
Plus
just right.
2 is root 3.
Uh-huh, everyone good? Okay, pi over 2.
0 and
0 and 2.
Okay, here's what we're going to do. When you sketch a curve parametrically, you'll notice something. When you sketch this, you still have the x and y axis. Notice there is no t-axis, okay? I'm going to sketch these points here with reasonable accuracy. This is the point 6, 0, okay? 3 radical 3, 1. I'm going to be roughly around, right around here, okay? This is 3 radical 3, 1. 3 radical 2, 3 radical 2, or a little bit higher. Okay. 3 radical 3. Pardon my lack of artistic ability, and 0, 2. Okay? Notice what's not on here. What's not on here is t. When you draw a curve parametrically, you indicate the t values by putting them right here. This point is t equals 0. This point is t equals pi over 6. This point is t equals pi over 4, and so on and so forth. And what's important is, more often than not, t is time. So when you sketch a curve defined parametrically, you want to show what's called its orientation. Note the arrows. Now, I'm going to move along here. I could extend this t-table all the way through, but in the end, what the curve is going to look like if I go and sketch the curve over its entire domain, it's going to look like an ellipse. Okay, hang on.
Every point's on an ellipse.
Yes, go. Okay? So what you need to show here, so make a note, you need to show the arrows indicate the direction of increasing parameter. And remember, parameter means the direction of increasing t. I think you probably have a sense of where I'm going. We're heading towards talking about motion, but not just rectilinear motion. Motion of a particle described parametrically. Everyone okay? All right? So if we were going to spend a unit on sketching curves defined parametrically, we would spend quite a bit of time on just this tedious exercise here. I think you would agree this is tedious. Plugging in t, finding x and y, plotting the points, sketching the direction of increasing the parameter. Everyone okay so far? We're with me? Can I move on? Yes, Alex.
This still isn't the graph of what it actually looks like.
This is the graph, Alex, of this set of parametrically defined curves. That is the graph of this.
It would be like, it's not going to be a circle every time.
No, I'm saying whenever we do like position graph,
Yep.
it's not what it it's not the actual motion of it.
Actually, in this case, it sometimes can be, yes.
But not always.
Not always, not always. Depends on the context. I'll show you examples in a minute. But my point is, boys and girls, do you understand how the bracket here, when you have a curve defined parametrically, you have to have x and y together, right? Like, you need to have, if you're graphing a curve on the xy coordinate plane, which we are, you always need an x coordinate and a y coordinate. Everyone okay? Yep. Now, let's talk about the derivative of parametrically defined curves. Obviously, even though this is not a function of x, you can see, look what I'm going to do here. You can see that I could conceivably go over here to the point when t equals pi over 6, and I can sketch a line tangent to that point. There is a tangent line, right? So the question is, if you have a set of curves, or a curve defined parametrically, the question is, how do I find dy dx? Dy dx is always and forever will be change in y over change in x, which is the slope of the line tangent. I mean, this is still the xy coordinate plane. This has a rise and a run. And if you look at this for a minute, how do I get to dy dx? Well, let's see. Let me recall something. We had this set of parametric equations. X equals 6 cos t, y equals, I know you see it, I know you do, Albert, y equals 2 sine t, okay? Now, I want you to look right here. What is the independent variable of x? T. If I were to take d by d blank of this equation, I'd take d by d what? T. Very good. Find me dx by dt, please, and find me dy by dt. We will pick up there. Yes, Daniel, go ahead.
So, when we're dealing with curves that are described using both x and y
Yep.
non-parametrically,
Yep.
like x squared plus 2y minus 3 equals
Yeah.
y, 2y's.
Right.
And when we use implicit differentiation to find a derivative, we have a derivative of dy dx.
Correct.
Now, is there a way to take dx by dt and dy by dt and merge them into dy by dx?
I'm going to answer that right now.
Oh.
I will never leave you hanging, Daniel.
Yeah.
I never will. If I ever do, you let me know, and I will make sure.
I never hanged in the first place.
I know. I will, and this is for all of you. If Miss Yam has ever led you astray, you will hold me accountable and say, Miss Yam, you led me astray. Daniel said, I know we've talked about curves defined implicitly. Here's a really big idea for a second. We've had curves defined implicitly. Here's question 1, who's not getting this question. When we had curves defined implicitly, those are not parametrically defined curves, because even if you have an implicitly defined curve, y and x are related in one equation, okay? Here, y and x are both individual functions of t. We'll talk about times when you can do what's called eliminating the parameter, not yet today. Daniel's saying, look at this. If I have, think fractions with me. if I have dy dt and I have dx dt, what can I do with this fraction and this fraction and be left with dy by dx? Cameron, what do you think?
Just like put -6 times I mean, divide that.
Yeah.
Let's see. If I say dy dt divided by dx dt, let's just check the math out. If I say dy dt divided by dx dt, and we are left with, boys and girls, dy by dx. The way that you will often see this is written this way, everyone. You will see this. Dy dx equals dy by dt over dx by dt. Okay? This is called dy dx of parametrically defined curves. Here, let's just finish the job. Let's not leave anything hanging. Here, dy dx equals 2 cos t over -6 sine t, or just -1/3 cotangent t. Look at that. Okay? I'm going to meet you in a second. I would like you to find, though, I want the actual slope of this line I drew over here. This one. That one. And I'll come back at you. Tell me how you find it. Go ahead. Daniel, yes?
So, ask a question.
No, that was you. Go ahead.
So first of all, when you said limiting the parameter, are you implying that all parametric curves can be written as inclusive curves?
Nope. Some can, some cannot. Yep.
And you also show us how to distinguish.
Yes, of course I will. I will never be hanging.
Okay.
Never.
And,
Yep.
So in this instance,
Yep.
We were sort of playing around with dy dt and dx dt almost as if they were variables themselves. So, first of all, can we consider dy and dt as variables, or can we not consider them?
I know. I need that's a question that I am going to leave you dangling for a little bit. Like the treatment of those differentials individually. Like Daniel's like, you just played awfully loose and free with these. Like treat them as fractions, just canceling them out. Yes. So we're going to dig. For right now, the answer is yes. There's going to be a time though when the differential in terms of t for one function cannot be regarded as the same differential t for another. When is that the case? It's an excellent question. Okay. That I will leave you dangling.
And then the other one is that, well, I guess building off of that question, second derivative can also be written as, if it be written as f double prime, second derivative can also be written as u squared y over dx squared. And
that's actually not the case. And that will blow your mind, but hold that thought. Ladies and gentlemen, what I wanted you to find, look at how I'm going to write this. I wanted you to find dy by dx at, what's the t value?
Pi over 6.
I have to see this. Thomas, why are you bellowing today, Thomas? What's going on with you?
What?
T equals pi over, is that pi over 6? Okay.
Hey, is it pi over 6 or is it pi over 4?
Which one was it? Help me. Okay. I need to see this. Look at this. You can't just, don't write ty dx equals and plug in pi over 6. I want dy dx at t equals pi over 6, okay, is equal to -1/3, oh my, cotangent of pi over 6. Oh, folks.
1.
No.
Isn't it pi over 4?
Mateo, redeem. Come on, let's go. Cotangent of pi over 6.
Pi over 6, which is sine.
May I?
I got it.
-3.
Yeah.
Cotangent.
Root
Got it.
I
think it's root 3.
It's just
-root 3 over 3.
Just root 3, but
Root 3.
well, so what's? Wait, so we have sine pi over 6, and that's 0.5.
there's just root 3. Just draw a triangle.
Okay, ready?
Right.
I'm not saying that one of the answers that were shouted amongst the morass was not correct. However, tangent of pi over 6 is what? Radical 3 over 3. Cotangent of pi over 6 is going to be 3 over radical 3, which you would then just go ahead and clean up. Okay? negative 1 over radical 3 at the end of the day.
Negative root.
Okay? Daniel asked a question.
So close.
He said, will the second derivative for parametric just be like d squared y over d squared x? No, it's not.
That's a shame.
To be continued. What is up with you, Thomas Muse? I've never seen you so sassy and brassy.
I really haven't noticed anything different.
You've been sassy and brassy.
It's a period 6 that Thomas actually isn't.